Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 3 on parallelization fundamentals. And admittedly, this comes a little bit later in the course, as it maybe should. But the idea is, of course, to give the assignment earlier with the MPI. And for this, you essentially need quite some substance of logging into the cluster with SSH, things we discussed around compiling C programs, which then, of course, have some MPI messages and message exchange functions to be called. So long story short, this is a bit out of sync to give the practicals an earlier start. And in order to review a little bit what we had the last time and the practicals and what essentially also awaits you in the assignment, let us review what we had the last time. And this was really a practical lecture 2.1 that was building on the conceptual aspects of MPI we learned in lecture 2. So there we had these interesting point-to-point communication, which was, let's say, one form of message passing that you do with this standard. There, the idea is, of course, as we know from distributed memory, to really basically transfer some data from the process memory from one to the other, right? Hence, this is not shared memory. This will come in lecture 4. But here we need really message exchanges to transport any form of data to the other processor. And we learned this in several different ways. One was this point-to-point communication, which in reality, if you remember some of the practicals, looked rather that we had a sort of buffer to be created, right? So when we have some data and we want to put it over the wire, in other words, to the other processor space, we need some system buffer for it allocated, and then it basically is sent over. So this is an important concept, this point-to-point communication, but this is not the strongest, let's say, from all the communication paradigms that MPI has. Instead, we use often collectives, right? The MPI collective communication that you also learned already in lecture 2, and we demonstrated a little bit broadcast the last time, right? Where we basically have one process or one task sending data to all the others, right? So this is something which is quite nice because it's scalable to the world of all processors that we have allocated in this particular job. So for instance, here MPI.com world with 10, let's say, tasks defined and asked for, so to 10 processors in a way that we can use. You can make the broadcast that you don't explicitly have now a for loop go, let's say, 10 times to a send and receive pattern. So in other words, you save a lot of source code lines here, right? By having a broadcast, it is automatically clear that the source is sending it to all other processors that are in the MPI.com world, for instance. We learned also, of course, you can do your own, let's say, subgroups. We have created the Cartesian communicator the last time as well, if you remember, where we then are able to have a much more Cartesian grid-oriented communication that is possible. But then when you look on the further aspects that we did, we use, of course, a C compiler and the scheduler that is shown here by the job script. We have also seen that the amount of processors enables us with the rank information really that although we all execute basically the same source code, we can differentiate. And this is, of course, another important aspect now of MPI, that although we have here in MPI.com world 10 processors, everyone gets a unique rank to know exactly who you are in this space. And this enables us something that you see here with a ping pong, quite a famous application, right? So 1 takes the ping, the rank 0 is a ping, and the rank 1 take the pong of the ping pong application just to transfer a message and back. Another important aspect, of course, when we looked at the coding, was also then the idea of having the MPI.com size and com rank field, which is one part of the elements. But also we learned that between MPI init and MPI finalize, which basically every MPI program has, is the time to do parallel programming, because before that you have just the serial space. So there's not the allocation that you asked for in the job script. Another element which was sort of important is exactly this blocking communication here. MPI send needs a matching MPI receive. And this is quite nicely viewed here in the ping pong, very simple. You can imagine that here is a ping starting and someone has to listen to the ping. Now this is important, right? So I made the analogy last time with a ball player, right? So if you pass the ball from one player to another, if the second one is not listening, is not paying attention, is not ready to receive the ball, you basically hurt him, or it will be just going somewhere. Hence, similar in MPI, we learned also non-blocking communication last time, a bit more an advanced concept. I don't want to repeat the whole lecture here, but I think these are the key elements in it. And then, of course, once we have done this ping with MPI send here, and it was well received from the other rank that has now received the ping, the other rank 1 here, is now basically able to perform the pong back. And of course, if there's a pong back, then the initial rank that actually sent the ping has to be ready to receive the pong also. Right, so I think these are important concepts. You see, we have to talk a little bit about what is going over the wire, what we really send in terms of data types, who is the destination source. And we learned also the Cartesian communicator gives us all this information if we are in a Cartesian grid. And today, we only want to review a little bit also the Cartesian communicator, but see the topic more broadly. Really engage in parallelization on a bigger scheme. Although it's a conceptual lecture, it has practical examples from applications where maybe the world is not always flat and grid. Maybe there are trees needed. One final concept that I also have shown you last time that I just want to point out, which is important, was a wall time in scheduling. Remember that the times that you put in the job script are really the ones where the scheduler thinks it's the job time. And everything, when the application continues running, the scheduler will just really delete, or basically better said, cancel the job. So this means you have to basically estimate the running time of your application to give the scheduler a better option to schedule all the other jobs also from all other users. If you fail basically to do so and your application takes much longer, you're running against the wall, as we call that. And this is here the analogy with the wall that you see there, which can be cumbersome. Let's say if you have a 24/7 I would say sort of running jobs, which is really taking a long time, maybe a week to compute. And then suddenly you realize that you need maybe more than all these hours you specified. And then you're running against the wall after have wasted lots of computing time over all the week. So very practical purposes today, a more conceptual lecture again, not really directly relevant for your assignments, but a little bit related. And we will basically see that there are common strategies for parallelization, which would be the first topic where we talk about examples, multi-core, many-core. We give very simple parallel computing examples, but then also we will talk about something which is an important concept in generally in simulation sciences and in parallel computing, which we refer to as domain decomposition, right? So the elements there is really tackle a domain which is quite large, computationally expensive, and we want to really think about how we crunch this into smaller problems. To do so, that's not always very easy. We have also Harlow and Ghost layers that we have to talk about then that basically mimic then this parallelization stream. So this will be part of the first element of the course. We will talk about the SPMD and the MPMD, which are sort of different paradigms how you can do parallelization, as well as data and functional parallelization. So you see lots of terminologies, and this will be actually in the second part even more. We will talk about several laws, which are quite important, starting von Amdahl's laws off to Gustafson's law, and also review a little bit what happened with Moore's law, which is quite known. And with all of this, we have a couple of terms that are really reaching into the theory of HPC, although we don't do this too much, thinking about scalability metrics. What does it mean to have a speed up? And also the load imbalance and so on. So let's go. So let's start with common strategies for parallelization. Well, parallel computing that we already learned in lecture 1 was all about solving a problem, a large problem, possibly in a cooperative way. That means we have this parallelization that we already talked about now in the course, that we have different processors. or if you want to say it also, you can see different processors, but also more notably speaking, different processes that running on this different hardware that is essentially now enabling us a parallel processing. We call it also sometimes tasks. Not really threats, because in the very lightweight with comes something which is much more than a topic of lecture 4. But by now you know that the idea, I think already from MPI and so on, that we now want to solve this problem by involving much more processors. And with this, we need to communicate between them. That's also what you already know now from practical lecture 2.1, for example. However, now let's tackle some of the ideas why we want to do this. That's something, of course, what we left a little bit out. Also, of course, here the idea is to have, let's say, the best possible performance. So performance is, as the name suggests, in high performance computing, a very important part. We have the top 500 list. I would encourage you, which are the, let's say, the most performance systems in the world right now for HPC. There are benchmarks that are done in order to get this ranking on this site, which is now an important part for you to look at. But inherently, again, this means also it's built from these different ideas of processors, more notably GPUs today, right? This changed a lot the pictures, and we will understand here a little bit why. And also think about maybe the bigger scale. So here you have one Lego brick, which was the multi-core CPU processor we already discussed. So here the, let's say, high performance comes really through the caches. We have high single thread performance in each core. So we talk about high performance just on a chip. But when you come to high performance computing, you leave the idea of just one chip. You basically combine many of these chips. And hence we have then many other aspects that follow suit, like the interconnect, for instance, which then also enables you to have low latency communication and so on. Just, of course, in the baseline, we would have this still as a basic building blocks, right? CPUs, GPUs, it's not that we don't use them, they're just differently aligned and basically also differently a little bit assembled in racks, very densely together instead of just somewhere in your laptop. Now, when you think about the parallel computing example and we want to solve a problem in a cooperative way, I think this is one of the small, tiny good example. You want to find the maximum in an array of 15 elements, 16 elements here. Of course, in production, that might be something like 10 to the 15 elements, not just here 16. So here you think now about the word domain decomposition, because what we have here is now quite interesting, a domain of 16 entries in an array. That's where the domain is. And okay, then we can now think about that, how many cores we have in order to actually break down this problem into smaller pieces. Right, and now the idea is that thinking about, we have 4 cores, that means each can have an equal share of a core set up by 4 elements in the array and determine what is the maximum locally, right? So basically that's what we can do. And then just basically from this information, we can find out what would be the global maximum. I think that's very obvious to find out. And the idea is now, by not using one core that is going through all the 16 elements, we use 4 cores in order to obtain something we call a speed up. And this is one of the motivation of parallel computing per se, speed up, having, let's say, high performance applications that are then faster in parallel than using a sort of more serial approaches. However, this is not always so obvious. You see here very optimized pictures. In reality, you would also see that someone has to do this max global. So it's not all equal shares that you see here, right? So that the max local A has the same, let's say, computing capacity as max local D. Maybe, you know, some of these in core 1 were also competing then with some resources in order to compute the max global at the end, collecting all the information. You know that from MPI now maybe perform a gather at the end in order to do then this maximum. And then this is something now, or we would say or reduce even with a maximum already inside the command. So you would use some collectives. And with this, you change the picture, which is now starting to something we call then load imbalance. But this will come over time, and we will make some points for it. Now, GPUs is something we already discussed here and there. You know by now it's a many core, so there are 1,000 processors of the core. And the key difference to the one I just was explaining is then that there are no big cache hierarchies. There's a device memory. There is something we call processors in the thousands, which is just of moderate performance, not the high single thread performance you have in a typical CPU, a number cruncher. And usually you have a long way through the device memory to the main memory to the host CPU. You will see that there are several new NVIDIA architectures. I mean, one is high bandwidth memory we will discuss, but more in lecture 5 then, and we talk about more GPUs in detail. But also GPUs have specific tensor cores now that actually enables us also to do more AI, more deep learning and scale and performance. So this all leads to the fact that performance can mean also sometimes several different things, right, for this term. Not only necessarily speed up, it could be also meaning for an AI model to have not only speed up, but better modeling, better accuracy, lower error rates because we do hyperparameter tuning, what we will also do later in the course. So the performance terms has to be also revealed a little bit in terms of architectures, in terms of what is the application goal and so on. Here you have a very good example again from GPUs. Why they are so good in AI these days? You have here an H100, for instance, from NVIDIA. Now we have the Grasshopper cards, which are already even more performance. And the way that works, even if they don't have the perfect processors, is exactly now the idea of the lecture. They have a domain, and this should be framing again an idea of a domain decomposition idea of a large, very large, maybe array that they want to multiply with a very large vector, which could be in deep learning really very large, right? So what you see here on the pictures just should, show you the kind of idea how you process this in the color coding, which is really independent from each other. You see everybody has a certain part only to compute, and there needs to be no communication between them. They can fill the resulting vector that you see here, A, by doing B times C according to the color code and can fill the cells very easily independently from each other. And this is sort of the success, why the GPUs are quite good in the performance in AI, for instance, because there's lots of matrix vector multiplications, matrix multiplications, where the mathematical rule beyond it is a domain decomposition that enables us to really be nicely parallel and to have not too much communication between us. So this is perhaps a little bit different, for instance, and that should frame again another domain decomposition term, where you basically have domain decomposition in here, very obvious, the Earth, right? So here we're talking suddenly about 3D grid cells, where the let's say physics, what you do, you see here physical processes as an example, right? There are many in one tile, as you can imagine. The Earth is very complex. But what matters usually is what you do in one grid part, yeah, and one of these small parts here. It matters also to the neighbor, and it matters to the other neighbor. So we have a problem here, which is not so nicely parallel, right? So basically, and you have here a very prominent example in numerical weather prediction, based on known physical laws, of course. This is something where you need the region around to be pretty precise about a grid part itself. In other words, you have lots of communication between your neighbors, right? And this is really a very important part of high performance computing as well. So it's not only the computing of the physical processes which are here meant to be accelerated faster. It is also the communication that you need then to be fast in order to say, well, I had rain so much and I had rain so much, so it's a high probability that in the next hour in main grid tile, there's so much rain, or whatever weather you basically predict, right? So in other words, your neighboring is important, and hence the domain decomposition has to be seen also a little bit in that direction. So there are domain decompositions which are quite nicely parallel. We have seen this with the GPU computing, but there's also domain decompositions like here, where the physical processes interact with each of the neighboring tiles. And this brings us also to some of the elements why we need message exchanges so much in MPI, what you do now in the practicals. So this would enable us in MPI now to talk to our neighbors, as you have seen in the ocean example I gave at the end at the practical 2.1. It's very close to the idea that we see here, It doesn't have to be the ocean wave height or the fish population we discussed. It can be, you know, the storm weather in terms of wind, in terms of rain. And you can add more and more physics to it in different atmosphere levels and so on. So simulating the Earth is pretty complex, as you can imagine, and a very good example of domain decomposition. Now, thinking about this, we should be seeing this term now a little bit broader and not very specific, because it could be different parallelization methods how I decompose my domain. And you see that in arrays, you can do it this way. You know, in long line, you can have arrays after a certain paradigm. You know, in a domain decomposition, we have seen the idea with a GPU. Then you would say you maybe decompose your domain, which is another important factor in this. Like here in the 3D grid, it could be somewhere in the Earth or our ocean again, maybe just, you know, not anymore 2D, but 3D. So then that doesn't necessarily mean that now every grid part has one processor, right? And core, like in the MPI ranks that we discussed in practical lecture 2.1. It could be still that the processor decomposition would be looking like this and having 8 pieces or 8 grid parts. So this is also something, of course, you have to think about when you do parallelization. And here are many other examples how you can arrange this depending on application logic. The one might be better than the other. And this is more sort of thinking about the data, the domain you want to do. We can also think about a way in which you have maybe different models that need to interact with each other. On a more higher level scale, for instance, here's a good example again from one of our elements where you have different models here interacting with each other. Each of them might be an MPI code, right? Being really in detail, having a domain decomposition like this. But then here we talk about functional parallelism, where this is all physics about atmospheric levels, hydrological levels, and then the land surface, how we interact with the Earth and with the ocean. So each of them has different physics to solve, but you see in the arrows, and this is now again the important part, they interact. So maybe they don't run a big simulation in terms of a one big thing, but rather, let's say, a very smaller part in different areas of physics that needs to be combined to get the complete picture. And then for AI, we have a complete other way of thinking partly, which I also will then show you more in lecture 6 and lecture 7 when we talk about distributed deep learning. There's again something called data parallel, model parallel, and so on. So when we look at this in detail in some terminology, and you have learned this now by far also with the MPI a little bit, we have executed always one single program, right? So it was always that, you know, the 8 processes we had or 8 tasks we had in broadcast, whatever, they worked in the very similar, you know, very same program. They just had different data. Every rank was different. So according to the rank and the data in the ranks, we could specify then that just one is performing a broadcast to all the others. Of course, this is a very tiny example last time. So of course, here in a big weather prediction, you can imagine that this is a much bigger scheme, but it's still one single program, one executable that will be maybe across 512 processes or 2048 processes, or even way more we will discuss as well. Then with functional parallelism, that's not the way, right? You would say normally would have maybe multiple program, multiple data aspects that could be going back here, for instance. There would be an atmospheric code, there would be land surface model code, hydraulical model code, and they interact with a so-called coupler from Oasis. This is something where, you know, we have some applications on this area. So there are different subtasks of the problem that solve the physics inherently themselves. And every now and then, of course, have to exchange some boundary conditions, some data, hence multiple data. But in the end, it's also different executable. And here we also see often the master worker scheme, functional decomposition, also coupling, which is a bit missing here. So you couple these different codes where, let's say, when you have 3 different applications, you would have a 4th application that manages all the message exchanges and the functional parameter exchange for it. Then when we come to another idea how you can do, you know, sort of parallel programming and also idea of data parallelism, you can think about much more source code ideas. And Shared memory parallel programming that we will have coming up now in lecture 4 for you is essentially this way of thinking, well, there's a big loop which is done by one, let's say, thread. And here we talk about threads in shared memory programming, and we will make the case more deeply in lecture 4. We had this already at the beginning of the course, but lecture 4 we make the case a bit more because you have always basically your shared memory address space you can access. And with a loop, this is just straightforward to say you let basically independently the loop run from 1 to 500 and then from 501 to 1000. And you can do this because you essentially do nothing else than having a constant multiplied by some vector, which is depending exactly on this index. And here also, right? You fill the result array also depending on the index. In other words, each loop execution is independent from each other, right? Except, of course, the E is accumulating to a higher value. But this is elements where shared memory is just beautiful, right? You put that on a different index, put it in the array. And by doing this, by using now different processors, really, that have access to the same shared memory space, you will then have a smaller execution time. But this has limits, as you can imagine. So think about always, like even with multiprocessors and the multi-cores, you don't have enough processors to maybe do now a numerical weather prediction, right, at scale. Hence, the physics that you can do with a shared memory is very, very limited. And with this, we come then also later then to the combination of distributed memory with shared memory, but we will make the case later for it. Hence, when we talk about data decomposition, you can have this on different areas, on different sort of levels. And here's one again also discussing a little bit how you exactly do it and forming sort of meshes. It needs to be not always Cartesian. In the icon code, we have actually hex-based, composition, or that you see here 2D grid display. So sometimes maybe that is good in the Cartesian world, and you go then to the 3D grid display, but in others you would not. So in the end, it's a very application domain problem, and also you have to think about how much end processors you have available to do this. And one thing that I want to make here also is the point with the physics again. You need to have variables that need to be stored per processor. And if there's a lot of data and it needs to be stored, the amount of memory might be limiting. Hence, you would maybe can even more compute, but the memory is full already. So you will have more processors involved, not because of the computing, but because the need of memory. The need of storing all of this information, which is, of course, for the scientists at hand doing this and for the engineers of the race cars as well, absolutely an important factor as well. Otherwise, it doesn't make sense. And there are different ways how you can do it. Some of them you already know. The ocean we discussed with the Cartesian grid 3D. You see here more advanced domain decomposition. We call that also adaptive mesh refinement. Sometimes it, depending on where the load is very much from the processors, more processors are involved than, let's say, in regions where not so much is to be computed. We have this in the race car, but also in the airplane here. And then even in simple setups, you would say there's still a choice to do, right? And this is, I think, what you see here a little bit, the 3D grid cell, where you store one information representing the cell, or you go to a more lattice display, where the nodes basically are just existing and so to speak framed from the values that you have around it that build the lattice. So you see it's a different way of simulating it, and it really is an application specific problem, but also think about the amount of data again that you here and there have to store. Maybe then it is more representative to have it as a grid, or you can have a smoother approach to physics by doing it in the lattice. This is really something where there's no one rule to rule them all. And here's another good, I think, example, making the case to our practical lecture 2.1, where now also computing capacity has to be put into the perspective, right? So in MPI, we were not thinking about this very much. We thought it's there. But if you have an application domain problem in terrestrial systems, like here, we want to simulate this ocean area there that you see, we have different choices and perhaps also different data, giving ground truth, giving data for the inputs. And, you know, the more and more I want to have more fine-grained, realistic behavior for the simulation, for the scientific computing over time, right? We need more and more resources. And this is, so to speak, a dependent project. It comes even to the point that you have to have more detail. Okay, what detail you want to add? Maybe today you add the boats, then you remove the boats, then you do the people, then you do the birds, then you do the oil platforms, or you do all together objects to study in this particular area, right? For logistic simulations, but also again, then in other simulations where it's about, you know, climate and so on, long-term climate aspects. This is all something where you have to decide a little bit the domain decomposition, the resolution, as you see here on kilometer scale, basically to what computing capacity you have actually available. Now then over time, simulating this and giving you then the opportunity to exchange between these different grids information you already know. We learned this in practical lecture 2.1, right? You do an iteration, and you basically exchange parameters in that. So from this, I want to stimulate you a little bit to a sort of orthogonal aspect to the domain decomposition, and this is time. So one of the key essence, even if it's in deep learning, right? Over time, we want to train deep learning models, or if over time we want to see a race car, you know, going through some area with, you know, interacting with the wind, understanding the speed, performance, bottlenecks of the race car, time is always there. And this is an aspect which makes it now much more complicated, right? We don't execute the MPI code once. Usually there's a sort of overarching loop, right? That goes time step by time step, time step by time step, advancing the physics, the location of the race car, but also the interaction with the environment. The same is true as a heat map in a room, right? So if someone now opens up a window in the classroom, what's going to happen? It's not something what we simulate directly from this moment where you open it to the end in one step. You see here after 200 rounds, we know how it looks like maybe in an hour. And this is something which is, again, an important factor. Firstly, the time is never necessarily to be equal than real execution time of HPC. So this 200 rounds could stand for half an hour in a room, in a classroom, or for 1 hour in the room of the classroom. So this is dependent on the physics variables. And secondly, in order to go to the situation that you have in a certain amount of time, you have to adhere, of course, to the values of physics before. You cannot just jump and simulate, in 1 hour it's like this. You basically usually have a time step behavior where you go through your domain decomposition. You will exchange information, what was in the time step before, that will have a major influence on the next time step, right? And if some of you are a little bit AI inclined, statistics inclined, it's similar like the Markov, a bit like Markov chains, Markov properties, right? You have this one Markov area obtained and then you jump to the next. Here we talk about different things. It's about evolution of physics over time, because many of the physics variables will be also having a time dimension to it, if not almost all of them. Hence the heat in the room we already discussed, but also there I wanted to show you that not each simulation is like each other. Here we talk about that maybe the simulation could be, you know, taken into account in a very rough way with 6 neighboring cells, or in a very accurate way with 26 neighbor cells. So lots of more communication also required here. This is a so-called Jacobi solver. It can solve the heat in a room application example. And it's so-called an iterative method in numerical simulations that basically step by step get you closer to the solution. It is not the exact solution. It is an approximation. And it is usually a formula that is well defined in basically in physics, which you see here, which is the, you know, diffusion equation that it is called. It is this change over time. And you see this right nicely here, how the temperature rises depending on other properties that you have, maybe the cold in the room, or basically the temperature in the room before you open the window, whatever it is. But there's a certain aspect I also wanted to convey here, and this is exactly what you see here with the arrows. You see quite nicely that time 0 is a time step now, basically, that we had already computed. But in order to inform what's happening on time step 1, the next one, we see very clearly that in order to compute the next time step for this particular area here in the domain, we need the information from the neighbors, and the arrows now show nicely what we have learned in MPI, right? So this is sort of now the time dimension to what you know in practical lecture 2.1, which looks a little bit like this on an isotropic lattice here. So this is kind of a nice domain decomposition. Some call it already also stencil code, because you will do the same for every cell, right? Like we learned also last time. But the truth is, you don't want to do this just like that. You have the time dimension, making it like that, right? So that means usually at the end of one of these overarching loops over time that you see here with 1,000 steps, at the end of one of such a loop, usually something like this happens, that whatever you computed in all the different tiles, you will inform your neighbors about it, right? Like here, for instance, but you do it from the results of one time step that influence the time step next, and then the new physics formulas will be applied with the new data of the time step before. And you see that a little bit with phi here at time step 1, it heavily depends on what was computed in time step 0. So one example formula, let's not go too deep into it, but this is an important part to realize when you come to this, that you need the information from the time steps before. And now, of course, this has a sort of dimension, what you see here also with the arrays and the values with K and E. This is now, of course, another orthogonal, and this is now really then going to performance tuning. How big are the arrays for these data structures? How much can we use shared memory versus distributed memory? Shared memory will be always faster, but it is significantly limited. We need distributed memory to scale. So hence, there's a big question mark, which you see here with a gray arrays part, to what extent we can use cache, to what extent we can use shared memory, and so on. And for that, I want to influence a little bit your thinking to this distributed memory approach, which we need at some point in time, which needs to operate the same way. If I leave shared memory and I have a situation like here, then I would need information which is practically not existing. That's why we call it a ghost cell, because it's somewhere in the other processor domain, somewhere in other memory. So what happens is that we introduce this halo and ghost layer, really, that is just for information exchange, essentially, and will be then taken up on the next time step for the computing of the actual data. In other words, if you simulate here the ocean, this area of the ocean is practically not existing. It is just to get some data structure for the next time step so that the wave on this corner or on this boundary here can be still well computed by the tile on the other side of the processor. And of course, you don't do this for one, you do this for every single one. They all exchange it in the ghost cells and the halo layer. And what you use, MPI for it. So there's another good usage example where MPI is often used to really fill the ghost layers or the halo layers with information. And also there, the domain decomposition matters. Although you see here one domain decomposition which looks like it is the same amount of tiles, right? But you will see with a gray, depending on how you do the domain decomposition, you have much less communication, right? So hence this blocky idea that we had in the beginning, you remember the ocean or parts of it that we then had in this 4 times block rather than long ones, means that from the physics perspective, we have to actually exchange much less parameters, much less communication is needed here, right? And this means high performance or more high performance usually, because less information exchange means less communication, and we can focus on the computing. And I know that is kind of bringing all together, means parallel programming is not the simplest. And I even left out a little bit the data analysis and machine learning domain, where you can end up like situations you have here, right? You have HPDB scan implemented from Markus Götz, one of my bright PhD students in the past. It's still one of the high scaling codes that we have, where you can clearly see that at some point in time, the processor domain maybe looks like the same space and you would cut it equal, but then you basically learn with the data in question, they're all on one side here as an example, and where you do clustering, right, that we discussed already in one of the earlier lectures. So you want to bring these points together, which are closer together. So this processor 1 is basically has much more to do in the end than processor 2. And to mitigate this, you would do some cost metric that you cut basically here in this interesting space already, because then the processor 2 can help processor 1 to digest all of these different points, because they have, you know, kind of Euclidean distances checked or whatever it is. It's quite an elaborate algorithm. We cannot go in all the detail here. But with this, you then can do more and more cores and get to a sort of almost linear performance if you adhere to these rules, right? So that you not just bluntly cut a domain necessarily in something what we as humans would see a very obvious, cutting it here in the middle. We will come back to this code again here and there. I think by now you have learned a lot about the domain decomposition, which was sort of goal of the first part of the lecture. For the master worker scheme, there will be also other lectures coming on later in the physics space, where we again go to this master and slave idea of workers. Somewhere in deep learning, we have this also. We will talk about this a little bit. So I would say this is topics which you have much more than when we talk about the CFD codes. They are solvers, they're solving particular elements like airflow, for instance, that you see here. And then we will also talk much more about how OpenFOAM and other multi-physics simulations then can simulate this. I'll leave you this video here to study our famous volcano, Eyjafjallajökull, that was here going over Iceland and then had an influence basically on the no-fly zone that you see in the video. There are other examples. I encourage you to watch the physics problems in this video, because not at all is everything in HPC still AI, right? So there's something where there's lots of other problems where you know, HPC is still needed, not only AI. We continue with some parallelization terms in theory then after a short break.